in this tutorial, we're going to work from a blank notebook. So we're going to import files. So we're going to import our file as the variable data. And again, import is one of our built-in functions. So we're going to use open brackets, and we're going to create a file path. Here's where there can be some confusion arising. Remember that Windows and Macs use a different a different file path syntax. So we're entering a path to find some data. And we're going to, after we give it a file name, we're going to use comma table, close brackets, to define that as a table. And that's useful for how we're going to manage that data later. So now we've created and now commented out a huge file of data, 460_kinetics.txt. And we'd like to create a new variable. This time we'll just call it T1, and we're going to build it from data, opening the brackets, and we're going to use all to look at all of the data in individual columns, and then follow that with a pair of columns, 1, 2 in braces or curly brackets. And you can see now that we created a XY data set, which we can go on to fit. But first, let's plot it. So remember, it's an XY data set. That means we're going to use list plot. And we just tell list plot in brackets to plot our variable T1. And we see that we have, in this case, this is enzyme kinetics data. So this is change in product as a function of time in seconds. New variable for modeling. So we're going to model this as a straight line. We call on the function linear model fit, which has a bunch of rules and background and bells and whistles. We'll keep it very simple, however, realizing that in linear model fit, we're going to open brackets, and we're going to tell it what variable we're using, and we're going to give it again, those linear parameters that we worked on last time. And this time when we execute it, we get the fitted parameters at the end. 0.003 intercept, 0.009 times x is our slope. So that's our standard output, and we define it as a model, which is going to be useful later. Right, and we can extract more detailed output by referencing model and then open brackets and parameter table. It gives us our table of this gives us a clear sense of the quality of our fits, for example, t statistics and p values. But for those of us that really want to see R squared, that's one of the widgets that you can learn about using from linear model fit as well. So remember, model accesses linear model fit, which we defined above. So there's our R squared valued 0.98. All right. Now, we want to show that plot along with the fit. So there's our, as we did before, there's our list plot calling our data variable T1, and then we follow that with a plot, which is a function, and we have to figure out the right way to input our function. We're just going to tell it to plot model, and we're going to plot the best fit, another detail of linear model fit. We'll look at other ways to plot that as well, but as everyone we use plot, we need to follow our target function with the range that we would like to plot. So in this case, let's make x from 0 to 20, close the braces, close the bracket again, it all looks good, and then we see our fit appear on our line. Oops, but we chose the wrong x range, so we can program that to go, let's make it all the way to 50, which is where the data seem to be going. So now we have our plot of our data and the model of that data, and we have estimates of the quality of that fit, and most importantly, of both parameters of the fit, the slope and the intercept. What else can we do? Let's get the slope out. Slope equals model. So we'll pull out the slope, and that's actually just giving us the whole function. So there's our, but we can extract the slope from that. We'll show you how to do that in a minute. But for now, let's just send out that function to a file. put append. Remember, we used this function in the previous tutorial. Put append is a built-in tool, Mathematica tool. We can read about it, but basically it appends an expression values at the end of a temporary file. We get to define the file name and the file path. So put append, always open brackets. We want to append the variable that we just created, slope, and we want to then with a comma and open quotes, and I think I'll just paste in the path from up above, just so I don't have to type it over again. There's our path, and we'll give a slash with a file name called test.txt. So in that file path, it'll create a new file. We've got to close parentheses, close quotes, close brackets. It doesn't tell us anything there. We have to go look at that file ourselves. So I'll open my Finder and bring up test.txt. You might have to go look for it if you didn't put it in the right place, or you just had accepted the default file location. But there you can see that it output one slope. What I want you to remember is that the original data that we imported, though, was many data points, not just a few. So in this case, the point of building up this model is so that we can iteratively fit all of the data at once automatically and output the results to a file. So let's see how we might do that. Oops, I think I put my slope append in the wrong space of your blank document. Doesn't really matter, but just to be clear, there it is. But now what we want to do is, yay, real programming. Oh yeah, and so I ran it again just to show you that when you run it again, it's going to append that same data, in this case, to that file. So you can imagine if you could tell Mathematica to create a loop by which it's going to walk through all of the functions, all of the data sets, you can quickly accumulate all your data without manually fitting. So we do that by creating a new variable, an iterator variable called I, and we'll set I equals 1. And then realize that what we really want to do is take all of these individual functions in all of these cells and put them here. So what are we going to do with I, though? So we'll use the while built-in function of Mathematica, and we'll open the brackets and say, if I is less than 9, then some stuff. And the first stuff is adding a number, adding 1 to I, so that I grows with every round of the loop. So you see all of these individual cells that we did work in. We want to bring all of those in to one place, and you can copy and paste them one at a time. I'll go copy and paste them from somewhere else. And this is exactly all the commands that we've already done, dropped inside our loop. Notice that our while loop is still open. While is still highlighted. We haven't closed that off yet. I'm going to change the path here to make sure it's going to the right place. Oh yeah, so the other important thing to notice here is that T1 is now not columns 1 and 2, it's columns 1 for our times and I, so that every time I iterates and grows larger, we create a new data set called T1, which includes a new set of XY points. We're calling this LM for linear model. This time it doesn't really matter. And then test is going to output the fit parameters. Just make sure we give a file name here. We'll just call it test_slope. And it looks that we got green lights on our function, so we're ready to run it. And you can see that the while statement is closed off. So everything that we did before is now enclosed in a while loop. Oops, something choked, cannot open, blah, blah, blah. It doesn't like something about the file name. Ah, that's right. So I have the path wrong. So I correct my path, run it again. I don't see any results, but I don't see any errors. So I can go open test_slope. And see that all those data are present. Every fit in our data set, 1 through 9, 1, 2, 3, 4, 5, 6, 7, I can't count that small. All of our data are there. And you can make sure that you don't need to change your iterations to capture all your data, but I believe we got everything there. So we created our first program where we can iterate through a set of data, act on each iteration, and get our output saved to a file that we can then go use. There's another way to do that, which is fun. I'll collect the while statement and drop it in a new cell. So we start off the same way, but we can, instead of using linear model fit, we can fit the data another way. So we'll create a new model. My model is a variable, and we'll set it to find fit is the Mathematica function that we'll use. Open brackets, we're going to act on T1, but now we're going to define exactly what the expression is, mx or mt plus b. So there's a straight line, followed of course by, followed by the variables m and b in braces, and then finally followed by the x variable, right, the independent variable t in this case. That's something that you get to define, however. So we'll close the brackets. Just reminding you that as you type, you can go learn more about the expression that you're using at that moment. And we can see that we're looking for the data, the expression, the parameters, and variables. In this case, the x coordinate. So we can go back and enter all of those again, find fit, open, blah, blah, blah. Okay, so, right, and now, critical, so it's all this, oops, what happened here? Go back, made a mistake there, find fit, open brackets, T1, mx plus b, where t is our x, comma, defining what our variables are that we're evaluating, m and b, close brackets, comma, what our x values are, and then we'll comment that out. We'll suppress that output with the semicolon again. And now I'll paste in the rest of my. Oh yeah, so yeah, we'll just put a pin. I will drop only the m value. I'm sorry, only the slope now. So we'll use this slash dot. That's a shortcut to tell it to pull m from my model, and it'll do that once per iteration. So it takes my model, pulls m out, comma, open quotes, drop in your new file name. You want to be careful to place your data in an empty file. You could get garbage really easily by cranking through this model as you debug your program. So we close that. The while is still open. We got to close that up. We close it. We add a bracket, and then we see that our open bracket is now not highlighted. Everything looks good. We can run it, and then we look at my model slopes.txt, and we see now what we have is a much cleaner file, only the slopes that we computed and nothing else. Very useful if you want to then go act on those slopes in yet a different model. So yes, we've extracted m from my model using the slash dot replace function. Save your data.